are coming to a public forum, and I'm happy that this number of persons are here to be a part of what we have been doing and what we want to do. They've spoken much about the Lacuna Fund, so I will not go there. But it's good that some of the ideas we've been nursing for many years was made possible by the Meridian Institute, that the founders of Lacuna. I'm supposed to talk on sustainable smart catfish spinach aquaponics farming in West Africa. West Africa, because West Africa is a tropical region. So, and the grant is supposed to, the data set generated here is supposed to serve the people of West Africa first. Now, why did we choose these aquaponics? The first speaker had told us the meaning of aquaponics. It's a system of rearing crops and fish in the same system at the same time. That's simultaneous rearing. It has a lot of advantages which we are going to talk about. But basically, I'm an aquaculture person. I'm into fish. And we know that global demand for fish has remained something that keeps on rising by the day because of increase in population and increase in awareness of the health implication of fish consumption as compared to the consumption of red meat. So both at local and at global level, the demand for fish has kept on rising. And aquaculture represents a potential solution for meeting the demand for fish. You know, initially we used to get our fish supply from the river and our water bodies. But consistent fishing has, you know, put pressures on them that they can no longer sustain the population. If you look at the water bodies around your place, if you are from a river in that around area, the level of catch in the 80s are no more the same with what you get now. It has reduced because of obnoxious practices and increase in fishing pressures. So because of that, aquaculture has come to fill the gap of demand and supply. And for us to do fish farming, there are lots of challenges. Challenges of feed and of water, especially in this part of the world where water table is very low. Water scarcity is a very big threat to sustainable aquaculture. And most of our farmers here will bear me witness that you cannot be buying water 10,000 naira for a tanker load and expect to make significant profit in the production of fish. And because of that, we started thinking, what can we do? And then the scientific community, all over the global scientific community, is thinking of how they could provide solution to water scarcity in aquaculture. And that's how the concept of aquaponics came up. A system that utilizes water and plant at the same time. One is it enhances water reuse and water recycle, as well as nutrient utilization in between the two organisms that are cultured. In a typical aquaponic system, the wastewater from the fish pond is recycled to the plant system, and at the plant system they pick out the soluble wastes from the wastewater, the fish pond wastewater, and then return purified water back to the fish pond. So in an ideal situation, if you are doing an aquaponic system, you are not supposed to change water. You can only top up the water, maybe because of water losses due to transpiration and all that. Now, the aquaponic system is relatively new here, but the guiding principle is that fish, we have farmers here and they will bear me witness that the prices of fish feeds are very expensive, much more expensive than poultry feeds. And you may ask yourself why. The reason is that the components of the diet of fish, especially the catfish, is very much high in protein, especially animal protein. And nutritionists here will tell you that the high protein diets are high in ammonia. By the time they are broken down, and the waste product that will come out from high protein diet will be very high in uric acid and ammonia. So in the case of fish, it's rich in ammonia. And ammonia is one of the most toxic chemicals in a typical fish pond water. I hope we're following. So when the fish takes it, they get ammonia, and ammonia kills them. And ammonia, in the presence of microalgae, is broken down into forms that are this fertilizer you buy from the market. A typical example is this chlorella lewin is an example of one of the bacteria that break down ammonia into nitrites and further breaks it down into nitrates. And the fertilizer you buy from your market is NPK. What is it called? Nitrogen, phosphorus, potassium. Now, that ammonia component is the nitrate that the plants can do what? Pick up, and it becomes what? Fertilizer. Now, in the case of fish pond, the ammonia is both ammonia, nitrate, and nitrite, as the case may be, are soluble waste. They are soluble in the fish pond waste water. So there is nothing you can do about it. You cannot filter it. Now, with aquaponics, we have designed systems that try to break down this ammonia into forms that, one, are less toxic, and secondly, are soluble and absorbable by the roots of the plant. That is this system. So when the water is bad for fish, we pump it up, and the root of the plant, we now do what? Pick it up, pick those ones that are bad for fish, and return the ones, the aspect of the water that will be good for fish production. That is aquaponics. Now, our project did not just look at aquaponics alone. We also looked at alternatives for space maximization. Some urban communities cannot farm fish in reasonable quantities because of space. If you're a tenant, it's difficult for you to farm fish. You cannot start laying blocks in somebody's yard. So we brought out the option of the mobile system. If you look at these ponds, please can you go down? Let's look at the ponds. Again. Yeah. These ponds can be dismantled and carried in your car boots within 5 minutes. So we started looking at the options of the use of polythene materials for mobile pond system, so that we can enthrone not just solving the problem of water scarcity, we're also looking at ways of making urban aquaculture very, very sustainable. If your landlord says you should go, within 5 minutes, you are gone. So some of our farmers here are using this system, and I don't think they're having issues with what they're doing. So we were looking at what stocking density will these structures be maximized, and at what population densities between the plant, that's the fish, and the plant population, and the algae, because we also generated microalgae that helped us break down this fish wastewater into fertilizer forms that the plant can utilize. Thank you. So what we did was we procured fish. You know, I'm a fish person, so I brought fish. Then we adopted please can you move? Yeah. We adopted an experimental design of a completely randomized block design. We have standards, but we have to vary the standards because we are now introducing a plant and a microalgae into our system. So what we did was that at each of those ponds, we varied the population. We had a treatment that we are stocked at the rate of 12.5 fish per meter square. The other one was 25 fish per meter square. The other one was 37.5 fish per meter square. And then out of these ones, we had constant plant population of 25 per plant bed. And our plant bed was measuring 1.3 by 1 by 0.2 meter cube. That was those beds you were seeing when the first presenter presented. Now, we had some controls. We had controls that didn't have plant or any identified or characterized microalgae. Just fish pond, normal, with the normal stocking density. Then the other ones had the 12.5 Now each of those ponds is 2 square meters. So 12.5 by 2 is 25. Then 50, 75. That's how we got to those fish populations you are seeing on the board. Please don't mind it. I'm not a computer scientist. So then we now had, because of the understanding we had with our funding agency, the Lacuna, they requested that these things we are doing should be replicated in farms, people that are already farming, so that we can compare results. And we had 2 outstation experimental units. We had one at Army Barracks and had another one at Enugu. So I think some of the farmers are here. We just mounted the ponds in their homes and allowed them to run it the way they run their normal farming system, so that at the end of the day we compare the results. So those are the treatments, E and F. The one at Barracks, we deployed the IoT and the aquaponics system. The one at Enugu, it was just a normal mobile pond. So we did pond preparation, normal. Most farmers are here. You fertilize and all that. We thought leave the poultry waste. Then we inoculated microalgae at the rate of 10 million cells per liter. And the microalgae we use is Chlorella lewini. That I must confess that it was very difficult to multiply them. I don't know what is happening in this part of the world, whether this is responding to the environment. But it's one of the most efficient microalgae in terms of breaking down the soluble waste in fish pond wastewater into a form that plant roots can digest. Then we also prepare the plant bed. Please, next slide. Now, I want to announce to us that this research has just started. We tried with amaranthus. That is, this is our vegetable. Now we have 1,000,001 vegetable crops that we're going to try with. And you know they have their own peculiarities. But for now, for the purposes of the timeline of this research, we worked with amaranthus. We are going to go into cucumber and so on. And I want to tell us that aquaponics works with vegetable crops. But it's difficult for them to work with maybe shrubs and other heavy feeding crops because of nutrient requirements. They don't go for, you won't plant palm tree on the plant bed because they are heavy feeders. The nutrient supply may not be able to sustain them. Then we also installed submersible pumps and water quality sensors, as my chairman has spoken. Then we did data collection and analysis of data. Then in aquaculture, we have some parameters we use to analyze the performances of our aquaculture species or the animal we are trying. And some of them are the weight gain, the condition factor, the normalized biomass index, and the formulas are there. Now, what are the results we got? Please go down. Yeah. These are results. If you look at our weight, you see what the result of the weight and then the percentage weight gain. You're going to see that treatment A had the list of the populations of 12.5 fish per meter square. That is representing 25 fish for that pond that is 2 square meters. You can see the weight, percentage weight gain. How it went up. Then the other one is the one that is 50. And then this one that is small is overstocked. So if you're doing either your aquaponics or even your normal mobile pond system, you are not supposed to stock that pond up to 75. So look at it. Then the E and F are the ones we did outside our main station, and you can see the performances. The performances were not significantly different from what we had at that population density. Then the condition factor. If we look at the condition factor, we can see that A seemed to have a lower condition factor. We are still trying to find out why. Then the 50 without any IoT sensor is also low. but the other ones are a bit high. Now, the ones we had at the outstation farms had very significantly higher condition factors. I don't know whether the farmers were giving them breast milk. So we're also looking at that one. And then if we analyze the weight in terms of the weight of the fish in terms of the weeks, we can see that we started expecting spikes in weights of the fish at 23rd week. At the 23rd week, we started having that, and it happened most among treatment A, which is the one with 25 fish. That's 12.5 fish per meter squared. Then the feed intake, the total, and then the condition factor 2. You saw that as the fish was aging, the condition factor was a little bit, sliding the curve, because their population and what they released into the environment was getting a bit more. So they also looked at the blood of the fish. That's hematology. And the blood, the treatment we had, IoT system, the aquaponics system, and I was talked at 25 fish per that is a 25 fish per meter for a meter square, and that one we had 12.5, had the highest what do we call it, the red blood concentration. So we're trying to use that to look at our result and compare and see the possibilities of the population stock, that's the population densities affecting the blood of the animal. We also looked at the white blood cells, and we saw that that one at the outstation where we had the IoT system had one of the least white blood cells. And the white blood cells are responses to stress. So somehow it seems they had less stress in the environment where they were reared. Now, there are many other things which time may not allow us to talk about here, but our observation at the research is that below 75, that is at 50 fish, that is 25 fish per square meter, the fish did well. Above it, 75, it didn't do much so well. Then 12.5 gave us the best of results, both at the aquaponics level and also at the mobile level. So the implication of this finding to fish farming in West Africa is that one, we had earlier talked about the water scarcity. We also talked about water reuse and recycling among fish farmers. Then space, problem of space and accommodation for fish and crop among tenants. That's tenancy aquaculture. We can do this aquaponics thing. We can do it, yes, but we need to look at the challenge of the generation of multiplication of the microalgae. And then okay, now we've been able to attempt to solve the water scarcity issues, and we are settling for 12.5 fish per meter square. And then I want to, because my challenge was how to merge the research findings presentation with what I will tell the farmers at the level of farming, because not all farmers are scientists. So it was actually a problem. But I will have to say something. What I have to tell us, which I had tried to say before, is that in terms of the fish pond, what we use is 2 meter square pond. That is 2 by 1 by 1 meter cube as the surface area for pond. Then the nursery bed is 1.3 by 1 by 0.2 meter cube. Then the smart appliances, which our chairman has spoken about, it depends on the one you want to deploy. Then the pumping system. There is something we do with the pumping system in an aquaponics system. That's what we use there that we call the bell siphon. Plants are specific to different levels of water logging. like this spinach, it has some number of hours that water has to, the roots have to be on water. Otherwise, they'll start decaying. Like that first picture we snapped was when we were doing trial. So we now have to develop a water siphon that has a number of hours. The pump will fill that bed, and it nature on its own it will trigger off and drain, so that the roots will be out of water to utilize what it has gotten. So the pumping system has to take care of the plant's water logging endurance or preference. So we used this DC pump 20. This thing is there. That's what we use for our work. Then the plant system, that's the plant species. The plant we use is amaranthus, and we say that we have the plan of trying out with other species of vegetable crops. Now the plant population is 25 at a distance of 20 cm. Now management of the setup. If you have your aquaponics system, it's not going to be jokes all the way. We had challenges in running the system, and one of the challenges is the pests. So we need to design a system that will either prevent pests or it kills pests. If you want to prevent pests, either you do a completely screened out system, or you apply bioherbicides or biopesticide, because the aquaponics system has the plant and the animal system. If you use herbicide to kill your plant, the pests on the crops, you are killing the fish. So that's the challenge we are having. So what we do is that we use biopesticides, and I don't know, one of the biopesticides we are using is you can combine the extract of ginger and onion and spray it there. It was chasing it away. But the best bet is to screen them away. You can build nets around it, and you screened your pests away. Then food and feeding. In terms of food and feeding, aquaponics is a system that when you're feeding your animals, you monitor the performances, and then the water pollution level, and then you also monitor the water. If we minimize our feed, the feed we give the animals with respect to the readings of the IoT materials. If our feeding, because of the protein level, is spiking the pH or other parameters, we reduce it, or we monitor the water. We can moderate with some other chemicals. So these are some of the things, but we have challenges to the adoption of the technology. One of them is high cost of infrastructure. These things are not expensive, but they are expensive. Yes. Then pests and diseases and algal multiplication. Then our recommendations is that if we can form cooperatives, it could help in getting these things at subsidized rates because of the power of bulk purchasing. Then pests and diseases. We talked about the use of organic pesticide and the screen or use of drugs. The aquaponics technology is new, but it's good and it can be carried out. Thank you very much.
Thank you, the presenter. You have done a nice job, and I think you have given us